Thank you. I want to begin by expressing my gratitude to the organizers that I may contribute to this meeting. And I also want to acknowledge in the beginning a cooperation. A great deal of what I'm going to say is based on a joint recent work with Tim Reetz. I will give the quote later, the citation, Tim Reetz. The role of mathematics in the genesis of the general theory of relativity is a special feature of that theory. It seems fair to say that, first, the general theory of relativity was the first physical theory to apply the formalism of tensor calculus, that is, Ricci's and Levi-Civita's absolute differential calculus, in an essential way. And second, it was also the first physical theory in which that absolute differential calculus was employed. In other words, the general theory of relativity emerged through a process in which an existing mathematical theory was applied to an empirical problem setting. The importance of mathematics in the emergence and early development of general relativity is also displayed by the role of mathematicians in that process of creating the theory. The mathematics of tensor calculus was introduced into the theory in the course of a collaboration between Einstein and his friend from student days, Marcel Grossmann, then a colleague and professor of geometry at the Polytechnic. The joint publication of the Entwurf, the outline of a generalized theory of relativity and a theory of gravitation in 1913, very obviously displays the character of their collaboration, showing a physical part by Einstein and a mathematical part by Grossmann. The role of mathematics is highlighted again by the competition between Einstein and David Hilbert, one of the leading mathematicians at the time, in that fall of 1915, in which the breakthrough to a generally covariant theory of relativity was made, and the centenary of which we are beginning to commemorate with this conference. And the role of mathematics in that process of constructing a relativistic theory of gravitation is displayed again by the role of the most competent and creative mathematicians or mathematically trained physicists in the early years of the development of this theory. Let me only mention here the name of Hermann Weyl, whose book on space-time matter was probably one of the most influential textbooks in the early dissemination of general relativity among mathematically minded scientists. Emphasizing that the role of mathematics for the emergence of general relativity played does not mean that this feature is unique to general relativity. Some very obvious cases in which mathematics played a pivotal role come to mind immediately. For instance, the interplay between the early calculus and the emergence of classical mechanics, or the function of elements from integral equations, matrix theory, and the theory of differential equations in the emergence of quantum mechanics. So given the significance of the role of mathematics in the history of general relativity, it should come as no surprise that in the historical commentaries, much attention has been given to the interplay between mathematics and physics, and the role that mathematical concepts and the role that mathematicians and their contributions have played in the early history. In this paper, I also want to address the issue of the role of mathematics in the early history of general relativity. I will try to look at the issue from a general point of view, and we'll be looking quite generally at the role and function of applying mathematics in the empirical sciences. The problem of the applicability of mathematics in the empirical sciences has long been discussed in the literature on the philosophy of mathematics, although it seems that perhaps the focus of that literature more often than not was on issues arising from pure mathematics. So some 50 years ago, Wegener published a now famous article entitled The Unreasonable Effectiveness of Mathematics in the Natural Sciences, that we've been quoted already in the talk before. And he wrote, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve." Wegener expressed his amazement about the applicability of mathematics in general terms. and he illustrated his claims by a variety of examples and instances. But it seems that the applicability of mathematics in the sciences really became a philosophical problem with the genesis of general theory of relativity and the emergence of quantum mechanics in the 10s and 20s of the 20th century. Sometime later, Mark Steiner elevated the problem of the applicability of mathematics to a deep philosophical problem, and argued not only for a distinction of different ways in which we apply mathematics, but also argued that it is not this or that instance of a successful application of mathematics that gives us pause to wonder, but it is the applicability of mathematics as such that is in need of explanation. In more recent years, the debate about the applicability of mathematics shifted somewhat away, perhaps, from attempts to give a wholesale philosophical account of applicability. Instead, the focus moved towards attempts to describe and analyze ways in which mathematics is actually being applied in the empirical sciences. In the following, I will also offer some considerations along this direction. I will briefly outline an account of the application of mathematics, and then use the categories of this approach to look at Einstein's actual work and ways of using mathematics in his actual research practice. So my talk will have 5 parts. I will sketch that conception, then talk about the Zurich notebook, say something on the return to general covariance, make some notes on the Japan diary notes, and end with concluding remarks. Christopher Pincock has recently offered an account of the application of mathematics that may broadly be called a mapping account. The idea here is that mathematics is applied to the world by means of structure-preserving maps between relevant empirical features of the world and parts of mathematics. A familiar, useful illustration of the mapping account is by means of a city street map. A city map represents part of the structure of a city by mirroring the street system and buildings of the city in some detail. Such a map will usually leave out some information, such as vertical slope, and sometimes it will not even faithfully mirror distances. However, there should be some correspondence. There is a mapping between elements of the street map and elements of the city, and therein lies its usefulness. Information about the city can be inferred from information given by the map. There are several systematic problems with such mapping accounts, which I will not go into here. In response to those difficulties, Bueno and Collivan have recently advanced what they call an inferential conception that may be regarded as a modification of Pincock's account. Here the main idea is to distinguish between mappings that map into the realm of mathematics and those that map back to the world. That is, they propose to break down the process of applying mathematics into 3 steps. In the immersion step, a mapping is specified from the relevant aspects of the empirical domain to the mathematical structure. In the derivation step, we realize mathematical inferences licensed by the mathematical theory about the immersed structure. This step takes place entirely within the mathematical domain. In an interpretation step, the consequences found in the derivation step are mapped back to the empirical domain. That is, we interpret the result of the mathematical investigation. Several features are worth emphasizing. The mapping of the interpretation step need not be the same as that of the immersion step. The distinction between the immersion and the interpretation step allows us to interpret the inferential conception in a dynamical way. The suggestion is that by going back and forth between mathematics and the world, one can gradually refine the mathematical description, and then one can also discover new empirical phenomena, or one can revise one's assumed preconceptions about the world. A third important feature of the inferential conception is the emphasis on the derivation step. The usefulness of mathematics in application can be emphasized by the inferential conception as follows, and I quote from Bueno and Colivan's paper: by embedding certain features of the empirical world into a mathematical structure, it is possible to obtain inferences that would otherwise be extraordinarily hard, if not impossible, to obtain. I should emphasize that neither are Bueno and Colivan the first to criticize morphism-based account of scientific representation, nor are they the first to emphasize the important role of the deduction of the inference step when it comes to scientific representation and modeling. Nor is the inferential conception, as advanced here, sketched here, free of systematic problems itself. The project, nevertheless, will be to take this inferential conception and apply it to various case studies in which mathematics plays a significant role. So this will be the project, and the examples that can be manifold, and those that come to my mind here are listed. For instance, Maxwell's discovery of his equations, Bose's derivation of Planck's radiation formula, and Einstein's transfer of that derivation to the case of a material gas, Heisenberg's Umdeutung, Schrödinger's search for a wave equation of matter, and then, of course, Einstein's and Grossman's search for a relativistic field equation of gravitation, the breakthrough to general covariance, and the search for a unified field theory. So in the following, I want to take that inferential conception of application and apply it to Einstein's work. The heuristic will be to use those categories and analyze what Einstein was actually doing, and at the same time remain open to the possibility that the inferential conception itself may have to be modified. So there immediately arises a problem, and now I wish I could do the trick that Jürgen did with the... So I do this like this. So famously, Einstein and Grossman had already considered in their Entwurf the Ricci tensor, but they had failed to see that it reduces to the Newtonian limit in the expected way. They write, wir müssen daher die Frage offen lassen. We therefore have to leave open the question in which way the general theory of differential tensors connected with a gravitational field links up to the problem of gravitational equations. So the cycle of immersion, derivation, and interpretation that constitutes the act of applying mathematics may not be closed. In fact, one may perhaps argue that in actual research, the unsuccessful attempt of applying mathematics in empirical theorizing may be the rule rather than the exception. So we therefore suggest to distinguish between open cycles and closed cycles. And I'm referring here to that recent joint paper, which hopefully comes out soon, but the preprint version is available on Phil-Sci Archive. With this distinction, the dynamical inferential conception provides a framework for the analysis of historical episodes in which the application of mathematics plays a constitutive role. In particular, it applies to those cases where the research process produces instances of application attempts that were, at least initially, not successful. The notion of an open application cycle provides the possibility to distinguish between several different problems or mistakes, because the problem can occur in any one of those three steps. We can map an empirical structure onto the wrong kind of mathematics. The mathematical framework may lack the expressive power that we need. It can be insufficiently understood. It can exhibit perhaps internal difficulties. And then there could be a failure in the derivation step. Certain inferences can be hard or even impossible to achieve. There can be mistakes in the calculation or in the mathematical argument. And there can be failures in the interpretation step. That is, by trying to interpret elements of that mathematical structure that have, for instance, no proper counterpart in the empirical structure. We also observe that the process of applying mathematics usually is triggered by some kind of problem or question, with the hope that applying mathematics may provide an answer to that question or solve the problem. And this trigger also constitutes a heuristics because it sort of carries over to the mathematical domain and gives direction to the explorations of the derivation step. It also creates expectations, standards to judge whether an application cycle actually closes or not. We therefore can also distinguish between subjectively open and closed cycles, that is, those where the judgment of whether the cycle was successful is based on the subjective opinion of the researcher, and objectively open and closed cycles. Usually only this can be done post hoc. Let me now turn to the first episode in which we see Einstein applying mathematics. The Zurich Notebook, as you know, is an important document that contains research notes by Einstein. In particular, it documents Einstein's and Grossmann's search for a gravitational field equation in the time between August 1912 and early summer 1913. That is, between Einstein's insight into the role of the metric tensor and the publication of the so-called Entwurf. The Entwurf is not really a jointly authored text. It's split into two parts, a physical part by Einstein, a mathematical part by Grossmann. And the Einstein-Grossmann collaboration allows us to therefore analyze the application of mathematics in terms of the collaboration between a physicist and a mathematician. And I couldn't refrain from putting an image there of the Einstein Zurich Notebook in the actual Einstein archives, which I first saw after we had published that book and had worked on this for years. And it really gave me chills to handle that paper physically, because you feel that applying mathematics is really something that you do and that leaves, traces on paper. So here are 2 pages from the Zurich Notebook that illustrate my point. From earlier arguments and physical theorizing, Einstein had come to the conclusion that the differential line element with the 10-component tensor field, G mu nu, provides an expression that has a direct physical interpretation in terms of the equations of motion for a material point. So this is page 05R, and here we see the differential line element. It may not be we've looked at these pages long and hard. So you see here's gravitation, and then there's the line element, and it says immer positive for a point. It's always positive for a point particle. And then he does the, he sets the Lagrangian and does a variational interpretation, and the Euler-Lagrange equations that follow from that ansatz give him, a physical interpretation of some of the terms of the metric. So he knows which one is the force, the momentum, the energy, just by looking at the Euler-Lagrange equations and identifying them. Now this other page, and we really don't know which one is earlier, because this one is the first one from the one end, and this one is sort of the first one from the other end, also starts with a line element, but here the process is completely different. It's completely stripped, for the sake of the argument, from its physical connotation, and it only appears as a symbol that is associated with a transformation property. So the mathematization proceeded by taking the line element and stripping it of its immediate physical interpretation and reinterpreting it in invariant theoretical terms. As a differential line element, it was a symbolic expression for an object that had its own existence in the mathematical discipline and of invariant theory. So we don't know precisely how Einstein phrased his question that he put to Grossmann in the early days of August when they started their collaboration, but clearly it was a call for assistance with any existing mathematics which provides information about the structural properties of a differential line element. So actually in the years of his death, Einstein recalled, and I quote, "The problem of gravitation was thus reduced to a purely mathematical one. Do differential equations exist for the GIK which are invariant under nonlinear coordinate transformations? Differential equations of this kind, and only of this kind, were to be considered as field equations of the gravitational field." The law of motion of material points was then given by the equation of the geodesic line. With this problem in mind, I visited my old friend Grossmann, who in the meantime had become professor of mathematics at the Swiss Polytechnic. He had once caught fire, although as a mathematician, he had a somewhat skeptical stance towards physics. End of quote. But we know the answer that Grossmann gave. Himself not an expert in invariant theory, he was nevertheless enough of a trained mathematician to recognize the nature of the mathematical problem and to identify the relevant literature in which the problem had already been discussed. This mathematical literature itself represented a tradition of mathematical research that led from Gauss's Theorema egregium via Christoffel, Grossmann's predecessor in Zurich, and his work on invariant differential line elements, as well as Riemann's generalized differential geometry via intermediaries like Bianchi-Lucat, the textbook on differential geometry, and Ricci and Levi-Civita's absolute differential calculus, to Grossmann's own exposition in the second part of the Entwurf. So in that process, Grossmann pointed Einstein to the Riemann-Christoffel tensor, and the famous page from the Zurich notebook that we've seen already by Jeroen displays just the kind of open application cycle that I had indicated in my introductory sketch. So, sorry about this. So we see Grossmann tensor vierter Mannigfaltig, Grossmann tensor for fourth manifold, tensor of fourth rank. Grossmann shows Einstein the Riemann tensor to Grossmann shows Einstein the Riemann tensor, and then we see a derivation step. Since the right-hand side of the field equation has to have only two indices and the Riemann tensor has 4, we need to contract. So this is the derivation step that we see here, and then we have an attempt at an interpretation step back to the empirical world, but we see that it fails because these 3 terms here that he also gets from that derivation step cannot be interpreted properly, and he says they should vanish. The episode is well known. In fact, this page was analyzed already in John Norton's classical 1982 paper, and the following pages of the Zurich notebook have been analyzed in some detail with a lot of interesting insights, which I do not want to go into here. Suffice it to say that from the perspective of this talk, and from a global perspective, the application of mathematics of the absolute differential calculus remained an open cycle. Einstein and Grossmann did not succeed in using the resources of that calculus in a way that would produce covariant gravitational field equations of the expected form. So to come to the third part, the return to general covariance, and I will be brief here and refer to Jürgen Renn's talk earlier this morning, and take their analysis and add some comments to it. So as we know, the return to general covariance begins on November 4 with the submission of this paper to the Berlin Academy on the general theory of relativity. And in the introduction, we've seen that quote already. Einstein write, "For these reasons, I lost trust in the field equations I had derived, and instead looked for a way to limit the possibilities in a natural manner. In this pursuit, I arrived at the demand of general covariance, a demand from which I parted, though with a heavy heart, 3 years ago when I worked together with my friend Grossmann. As a matter of fact, we were then quite close to that solution of the problem, which will be given in the following." So I will make use of my comments on this earlier presentation, and so Michel Janssen and Jürgen Renn detail their chapter and title it with the phrase "untying the knot," and they write, quote, "Our metaphor is not cutting the knot, but untying the knot. We argue that Einstein found the field equations of general relativity by changing one element in a formalism he had developed in 1914 encoding the various physical considerations that had gone into the derivation of the involved field equations, end of quote. So the untying the knot metaphor has been a productive one, and its suggestion that there are elements to the conceptual structure that hang together in various ways, that most of those links remain intact over that process of restructuring. From the perspective of the dynamical inferential conception, another perspective is suggested to look at that problem, and that is the perspective of looking at this as a mismatch between an empirical structure and a mathematical structure. So the failure of an application cycle to close may be located, as we have seen, at various places. And by the way, this is my summary of your paper. So we have here the energy momentum conservation balance in the Entwurf version, and this form sort of suggests that this expression here is what represents the gravitational force, and then we have more or less the same relation here written with the Christoffel symbols in their full beauty, and the transition between this and that is taking assigning a different element of the formalism to the empirical structure, and by which everything falls into place. And the same thing can be done in various places, for instance, in the Lagrangian of the variational principle. But if you do it here, you're not doing something essentially equivalent. You're producing new field equations. Let me briefly remind you of the difficulties that Einstein had encountered in the process of elaborating the Entwurf theory. For one, we know that he did not reproduce the correct or the empirical value of the Mercury perihelion, which is clearly a failure of the application cycle because it cannot be interpreted empirically in the right way. Second, and the next two problems are indications of this mismatch, he had discovered, we know that from a famous letter to Freundlich in September 1915, that there was an internal inconsistency in the way that the Entwurf equations handle the case of rotating Cartesian coordinates. And third, 2 weeks later or so, he found that the alleged uniqueness argument of the derivation of the Entwurf Lagrangian proved illusory. And with those three problems, Einstein lost faith in the Entwurf theory and went back to the drawing board. And I'm just referring to the talk earlier this morning. So the technical details of that reinterpretation are involved and cannot easily conveyed in the talk. All the details can be found in the chapter Untying the Knot. From my perspective, the reassignment of an interpretation of one of the elements of the mathematical representation is to be seen as an instance of closing an application cycle by fixing the interpretation step. So I totally agree. There is a great deal of the deductive structure of the Entwurf in its most elaborate form of the Formale Grundlage of 1914 that remains intact in the process of returning to general covariance. The stumbling stone proved to be a wrong interpretation step. Once the elements of the mathematical formalism were reassigned with a different physical meaning, the application cycle closed and everything fell into place. There's also, to be emphasized, two other features. For one, the fact that the solution was prepared by a process of realizing a number of implications of the mathematical formalism that were unknown to Einstein from the outset, and this process involved, in particular, the reformulation of the Entwurf field equation and its derivations in a variational form, which sort of brings together an additional or new piece of mathematical structure. Sorry. From the perspective of the dynamical inferential conception, the empirical structure and the mathematical structure act on a par. Both allow for inferences and derivations, and both create and determine heuristics. But there is, of course, a systematic difference. The empirical structure is determined to a large extent by experience and empirical validity, and the mathematical structure is not determined by empirical meaning, but by axiomatic and inherent consistency. The mathematical structure therefore displays a different kind of rigidity, a rigidity of its conceptual interconnections that can only be broken by pain of self-contradiction. I therefore like to think what happened in the fall of 1914 was a process in which the inherent logical rigidity of the mathematical structure exerted its power and showed that one can only interpret a given mathematical formalism by wrong assignments of physical notions with elements of that structure to a certain point. At some point, inconsistencies and contradictions become all too obvious. And since we know that the tensorial formulation objectively provided the right kind of mathematical representation, it seems that Einstein indeed had to revert to the mathematics of the Riemann-Christoffel tensor after giving up on the inconsistent and Wolf logic. What is important here for our purposes is the way that Einstein viewed and utilized the mathematical representation as a means of realizing implicit consequences and connections, and of interpreting these by assigning physical meaning to certain elements of the mathematical structure. In this instance, we see that the closure of the application cycle came about by reassigning a different physical meaning. So I will now say something about the Japan diary notes. I want to focus on a manuscript that has a very similar character as the Zurich notebook, except for the fact that we cannot analyze it as documenting a key step in the process of Einstein's greatest success. The efforts of the analysis of the Zurich notebook were justified because it allowed us insights into a research process that eventually resulted in a successful conceptual transformation that is at the basis of today's understanding of space and time, and that led to the formulation of the gravitational field equations that are still being tested, that we still believe in, and are still being tested in multinational and multi-institutional research efforts. So the manuscript that I want to comment on now is of a different significance. It too documents Einstein's thought process in a rather direct and coherent way, as does the Zurich notebook, but its problems and insights remained largely inconsequential. The notes I'm referring to are found in the back pages of the travel diary that Einstein wrote on his trip to Japan, Palestine, and Spain in late 1922 and early 1923. This is his itinerary of that trip. He starts off from Marseille and then is on board the steamer to Japan, where he stays 6 weeks, and on his way back he stops for his famous visit in Palestine and goes back to Berlin. The travel diary and the notes are contained in volume 13 of the collected papers. The context of these notes is a paper that Einstein published in February 1923 in the Proceedings of the Berlin Academy, and it's entitled On the General Theory of Relativity. There's also a manuscript of that particular paper, which is dated to early January 1923. On closer inspection, there are significant differences between the manuscript version and the published version. We know from Einstein's travel diary that he had penned the manuscript of his paper on board ship on his return, but then withheld it at the last moment because he had found a flaw in the argument. So he had penned the paper to mail it on a stop in Singapore, but then he withheld it and then wrote these notes, and the version that got published, it was mailed when he entered in Port Said. So we know these notes were written on this leg of the trip. In a sense, these notes provide a laboratory of mathematical thought, because we see Einstein at work in a situation where he's largely sort of out of context. He's on board ship. That is, he writes the manuscript in the first day of his return journey, then decides not to mail it, but to rework its argument. And by the time he arrived in Port Said, he has settled on a new version that he sends to Max Planck. While we can see that there were no distractions or interventions in Einstein's thought during that trip, during that period, he did engage with existing literature. Two books that he probably brought along this trip were the 5th edition of Hammond-Weil's Space-Time Matter and the proofs, maybe, of Eddington's Mathematical Theory of Relativity. These books, in any case, span the problem space of Einstein's manuscript. So the problem was this: the gravitational field equations of the general theory of relativity in 1915 were originally formulated in terms of the Ricci tensor, which in turn was conceived as a function of the metric. So Eddington and Weil had taken the analysis of the mathematical foundation of the theory a step further by focusing on the affine connection as an independent mathematical concept. Both Eddington and Weil were motivated in this effort by hopes of constructing a unified theory of gravitation and electromagnetism. And we know that the pertinent paper that contains Eddington's ideas on this of 1921 was known to Einstein because they had communicated about that paper during Einstein's visit in England in 1921 from that correspondence. If we now look at Einstein's travel diary, we see indications of the progress of his research. So these are comments from his travel diary. He writes, on the first day of his return journey on 30 December, peaceful trip, idea for development of Weil-Eddington theory. 3 days later, he says, pondering and calculations on Eddington's theory, attempt at a completion of the latter, improvement of the variation method and regular general relativity. 3 days later, a new idea for the electromagnetic problem of the general theory of relativity. Again, and then thinking about general relativity and electricity, and then 9 of January, writing paper on gravitation and electricity, and this is why we know that this particular manuscript was completed on January 9. And then he writes the next day to Niels Bohr, I now believe I finally understand the connection between electricity and gravitation. And then 3 days later, he says, oh, I discovered a fly in my electricity ointment in the afternoon. A pity through tropical heat. Ein Haar in meiner Elektrizitätssuppe in German. And then he continues, he's 2 days later has new ideas about the electrical problem, and then 3 days later, disciplined toiling on the problem despite the heat, moving forward with many setbacks. Final draft 22, January 23. In the original formulation of general relativity, let me try to indicate what, in my understanding, in my reconstruction, was the problem that Einstein had discovered on January 13, 1923. So in the original formulation of relativity, as advanced by Einstein and Hilbert and others, the basic variables were the 10 components of the metric and the 4 components of the electromagnetic 4 potentials. A variational formulation of general relativity allows a derivation of both the gravitational field equations and of the Maxwell equations if you vary the action with respect to the metric and the electromagnetic potential. So here you have the green one is the gravitation part with the field equation of the Einstein equations. This is the Maxwell part with the Maxwell equations, and if you do the variational principle, both these equations follow from the variation with respect to, if you vary with respect to the metric, you get the gravitation equations, and if you vary with respect to the potentials, you get the Maxwell equations. A flaw of the theory in Einstein's as well as others' understanding was the fact that gravitation and electromagnetism entered only additively in the action. So here there's only the sum of the Riemann curvature scalar and of the electromagnetic part. And that, in Einstein's understanding, expressed only a superficial unification of both fields. And in our context, it is also important to note one feature of classical Maxwell theory, that is, you can have non-trivial fields in the absence of sources. So it is not the case that if the sources vanish, the fields also have to vanish. So the idea that Einstein was pursuing on board ship on his return from Japan was, I think, to follow Weil and Eddington in their suggestion that the affine connection is a mathematical concept in its own right, and largely independent of the metric. So the heuristics is to engage in a different application cycle and to explore the possibilities of a mathematical representation based on the notion of parallel transport and affine connection. So he starts now from the concept of parallel transport, where the independent new variables are the coefficients of the affine connections. They are now independently given, which means that the Ricci tensor turns out to be asymmetric even if the connection is symmetric. And if the Ricci tensor is asymmetric, it splits into a symmetric and an antisymmetric part. And you can now conjecture, and that is sort of the immersion step again, that the antisymmetric part of the Ricci tensor following from the from the connection coefficients represents the electromagnetic fields. And the currents, since we don't have external currents, the currents are expressed as the covariant divergence of the field. So, so then he applies the variational principle, and so what he does is he starts from a Lagrangian which is assumed to depend independently on the metric and on the connection coefficients. And then the formalism says if you vary the action with respect to the metric, you get the gravitational field equations as earlier. And if you vary with respect to the connection coefficients, you get compatibility conditions for the metric and the connection. Now he does that for the pure gravitation case. So he takes as the Lagrangian the pure Riemann curvature scalar, and he does recover what conventional general relativity gives him, namely the vacuum field equations and the compatibility conditions, which indeed determine the Levi-Civita connection, because the Levi-Civita connection is the one that satisfies this condition. Now, the next step would be to add electricity, and he does that by tentatively adding an electromagnetic term that is modeled after what he knows from standard electromagnetism, a term like this. And if he does that, he recovers the Einstein equation, the gravitational field equations, and he also gets compatibility conditions, which now look a little bit different. So far, this is the argument as I see it from the manuscript that he writes on November 9. Now, I think what he discovered in the following 2 days is that if you take that compatibility condition and plug it back into the definition of the current, this is a little bit more involved calculations, then you see that you get this relation. The field tensor is related to the derivative of the current, and that means if you have no current, you have no fields. And that's the contradiction to standard electromagnetism, and there the interpretation step fails again. So just to show you how this looks in the manuscript, so this is where he does the variation of the action with respect to the metric and the connection, and basically this is Palatini's method. And then here's the page where I think he's reacting to the mistake or the problem that he had found, the difficulty. So he says we split RAK into a symmetric and antisymmetric tile part. One can assume that AIK be the electromagnetic field, but this leads to difficulties. And now the reaction is that he reassigns, he tentatively tries out a different immersion step by taking still the same mathematical structure, but kind of putting a different mapping onto it by assigning different pieces with the structure. In any case, he reworked the paper, and this is the paper that he then published. And we know that after his return back in Berlin, he continued working on that approach, and he published 4 more papers, and there are also more notes and comments on this, which will be available in volume 14. And I just want to read this quote here. He gives up the approach in sometime in late summer 1923 for good, and he writes to Weil, "I'm sending you here the proofs of my new paper, which I have to publish because Eddington's idea has to be thought through to the end. I now believe that all these attempts on a purely formal basis will not bring our physical insight any further. Maybe field theory has already given everything that it was able to give." So what is significant in this episode for our purposes is to see that Einstein again follows a certain methodology. Again, he tries to apply mathematics by utilizing the inherent deductive capabilities of the structure of a mathematical representation. We also see him very consciously dealing with the formalism in a certain manner. He very explicitly assigns physical meaning to elements of the mathematical representation and then tries to exploit the deductive possibilities of the representation in attempts to rederive or known results. So, and I think I should conclude with some comments. I have in my comments on all these 3 episodes, I have presented Einstein as handling mathematics in a particular way. The working hypothesis is that Einstein's research methodology can sensibly be described in terms of the dynamical inferential conception. That is, in terms of open and closed cycles of taking immersion steps, derivation steps, and interpretation steps. If that dynamical inferential conception provides a reasonable framework to analyze and interpret episodes like this, in which the application of mathematics plays a significant role, one should be able to describe Einstein's work in these terms, and I think the project is feasible. The question, of course, is, can we capture also the specifics of Einstein's approach? And this, of course, can only be done by comparing it to other researchers. And I, of course, an obvious case to look at is the Hilbert and the Göttingen community. Felix Klein, he has 2 quotes by Hilbert on Klein. Perhaps one way to characterize the difference in the methodology of Einstein and Hilbert in terms of the application of mathematics is this. Einstein largely took the mathematical theory as a given resource for his inferences. He did try his hand at inventing proofs in a mathematical sense, but at least in the framework of the Entwurf, his proofs turned out to be flawed or didn't hold out. And he reflected explicitly on that failure. Einstein's emphasis was on the interpretational side, and the mathematical representation was a means to describe and derive features as a given. And in applying mathematics, he put his efforts into rederiving known results or in order to establish empirical validity. Hilbert, in contrast, largely took the empirical results as a given, and in applying mathematics, put his efforts into rederiving known results in order to establish empirical validity. As a mathematician, his concern was with the origin of the mathematical theories and their axiomatic formulation and foundation and their inner consistency. An inconsistent mathematical theory is meaningless, but an elaborated mathematical theory provides a rich resource of mathematical structure for the interpretation of the world. So given the fact that neither the laws of nature nor the logic of mathematical proof depend on subjective will, I think both conceptions appear to be complementary to some extent for the analysis of mathematized empirical theory. And I want to conclude with this quote from a letter that will be published in volume 14. It occurred to me this morning that this is another instance of the word schön. Even though it might occur ironic, I don't think it is. So he says, mathematics is schön, beautiful, and good, but nature kind of leads us astray. And then he said the whole thought, the whole thought has to be taken to the conclusion, and is of, of strange beauty. But above there is the marble smile of, can you help me? Of the forceful nature which gave us more longing than wit. Thank you.
Merciless nature.
Thank you, Tilman, for a very nice talk. I have a question regarding the inferential model that you used. Could you show the image? And so,
Sorry.
yes, no.
This one, right?
Yeah, I guess the bottom one is the same as the main one, right? So if this applies to Einstein, then how about the following? How about you rotate it 90 degrees and the world becomes a line, and then everything stays the same, and then maybe the deduction arrow also gets also rotated. The point I'm trying to make is, isn't this kind of the same diagram that he drew for Maurice Solovin?
I don't have that. Maybe.
It seems like the same diagram he drew for Maurice Solovin.
I don't retrieve that image now.
So my naive expectation would have been that Einstein would be excited rather than disappointed if he got rid of source-free radiation in Maxwell's theory, because that would be a kind of electromagnetic Mach's principle. Do you think that's... Am I thinking about it the wrong way?
Yes.
Well,
okay. That's a complete answer.
No, we can go into the details. The support for Maxwell theory vacuum solution, which explain observable facts, so you wouldn't.
Yeah, I'm not sure Einstein. Well, I mean.
sure. I mean, so far he was happy, and he penned the paper ready for publication. What I kind of didn't elaborate, because it would become very technical, is that last step. When you get that additional compatibility condition between the metric and the connections, when you add that tentative electromagnetic source term, and then you plug that back into your definition of the source, then I mean, this is my reconstruction. Then you get this result, and this he writes. I infer this indirectly from the published paper, because he says there that it's a problem that it would follow from this that you can't have fields if you have no currents. And then he goes into a strategy where he adds a factor that has to be very, very small so that you can still have sources. And so he kind of reacts to this. But this additional step where he kind of loops back this argument to interpret the new compatibility conditions in that, I mean, it's an interpretation step, in that additional immersion gives him something that he can't interpret with what he thinks is a basic feature of Maxwell electrodynamics. That's my, I mean, it's a reconstruction.
It just seems so different from his reaction to the fact that asymptotically flat solutions have applications. Right?
Yeah, yeah.
Yes, but that's because there's some, around here there's those kinds of boundary conditions, but in a real theory we should get rid of that kind of stuff. And
that I don't see in his calculations. I mean,
So I have three more questions. One is Jeroen, one is Denise, and one is Robert. And if anyone could...
Sorry, Gordon, for the... Sorry for the brutal.
it's always good to have the truth.
Thank you. So my it's rather common. It's a follow-up on Gordon's question. I think so. Even when Einstein was very deep in his Machian phase, so before de Sitter found the first proper vacuum solutions, at that time, much very different from later in his unified field theory phase, when he thought basically the electromagnetic field and the metric fields are ontologically on a par, right? They're two separate, ontologically separate fields that we now have to unify. When he was in his Machian phase, he seems to have seen them as very different in a sense, because back then he was sure that the electromagnetic field had independent degrees of freedom, and so it was a physical entity in its own right, and it was supposed to have dynamics that are not entirely determined by the sources. For the electromagnetic field.
You're saying, like, even in like 1916, 1917,
Yeah.
1918,
Yeah.
you thought that the electromagnetic field had its own degrees.
Yes, very much in contrast to the gravitational field in his mind in that era, where he thought it doesn't have independent degrees of freedom. It's derivative of the material degrees of freedom. So that was why he never expected, I think, something like a mass principle for electromagnetism, but he did expect it for the metric field. And then that changed later with the vacuum solutions and his realization and admitting that the metric field also had independent degrees of freedom.
My question is not related to this issue, but to this diagram, so maybe I put it shortly. I like this very much, what you have done, Tilman. I only have an objection, maybe a little bit to the terminology on this graph. But it's a very limited objection. It's lost it again, the connection. Can you? There it's coming back. And it's because the notion of mathematics behind this graph seems to be too static. Also, you know, because you talk about deduction and application, as if the world of mathematics would be just a crystalline structure out there. And of course, it's evolving all the time. And Einstein and Grossman themselves, the kind of tensor calculus that it's kind of a syncretistic, you know, further development of the absolute differential calculus, mixing it with the traditional vector calculus and the tensor calculus from crystallography. And this happens all the time. Mathematics is a moving target here. And, and speaking about deduction makes it too axiomatic formal. Speaking about application, again, as if application wouldn't have consequences for the formalism itself, beyond the issue of identification. But I'm sure you know this. But
no, you see me nodding along to what you say, because in that paper we do make exactly that same argument. We look at Grossman's contribution, and we distinguish between what we call an a priori mathematical development, which leads from Christoffel's very abstract first introduction of the Christoffel tensor to the Ricci-Levi-Civita. It's an internal dynamics within mathematics, from a very abstract piece of mathematics of invariance theory to something that is actually within mathematics conceived as a calculus to be used by physicists and to be applied. So there's an internal mathematical development, and there's also a subjective work that Grossman does in appropriating that resource, where he kind of takes the Ricci-Levi-Civita system and puts them turns them into tensors, changing notation, introducing the Ricci tensor. So we do emphasize that it's just, you know, for the
that cannot all be subsumed under the heading of deduction, of course, what you just summarized here.
No, I can't, although we tend to have a broad notion of all these three.
That's
That's the last question. You wanted more time. Were you fast in covering? Yeah. Okay, so
my question is also related to to what I heard in Jürgen's talk. It's about the Japan manuscript from 1923 and 1924. I understand that, as Jürgen said, that Einstein needed the Levi-Civita connection in order to derive the general covariant field equations before 1916. And he lacked this connection, and therefore the closest thing that he had is the Christoffel symbols. And once he had this connection, then he had the required tools, and he derived the vacuum field equations, and as you said, using the Levi-Civita connection. And then you said that he that after 1923 he simply chose a different way. Am I understanding it correct?
Sort of, because what in his understanding, what happened is that the affine connection, which in the meantime had been elaborated in various contexts, for instance, in space-time matter, in a very elaborate first attempt by Weil to formulate a unified field theory. It had kind of been elaborated and advanced, and what he perceived in Weil's and Eddington's work, and this may be something that you could see differently from a broader perspective, but what Einstein perceived in Weil and Eddington was a suggestion to take the affine connection as an independent mathematical concept, and take that and to dissolve the link between the metric and the connection that was encoded in the Levi-Civita connection, solve it and treat both quantities as independently given and independently given meaning in mathematical structure, and see what that structure provides in terms of resources for physical interpretation. And that is something that is completely different than what you had in 1915, I think.